Alrighty, I am recording this from a very dark living room. I got my Christmas lights on, but you probably can't tell. And I'm all scrappy because I was just running with Marathon High and just like came home and was like, let's just do these videos and get them prepped. This particular presentation, I did not mess around with. I didn't really add anything to it because it replicates the NAND presentation except with NOR gates. And so pretty much every piece of this mirrors the NAND presentation, and the longest part of it is working through the example problem. If you paid attention to that lesson and got that concept down, this one should come fairly quickly. So it's really the same idea. So the presentation covers the basic function of a NOR gate. Again, like just with the NAND gate, we've talked about it, but we haven't done a whole lot with it, so it's worth reviewing. Then how you can use it to implement the AOI logic, and it's very similar to the NAND, just two pieces of it are flip-flopped. And then we'll go through the example with the circuit. It's the same circuit from the last lesson, except instead of doing NANDs, we're going to do NORs. And you do see that there's like an advantage of one over the other. So if you were working for a company and you were going to do a universal gate design, this might make a difference. Like, should you choose NAND or should you choose NOR? Like, which one is going to be better? And then we'll go through the IC and the chips. And again, you'll see that there is an advantage of one over the other. So basic function of a NOR gate is it ORs and then it negates. So if you figure an OR gate, that's awful, takes two things and ORs them together like so. Okay, that's an X and a Y. Again, I'm doing this in a very dark living room with hungry cats. Like, my cats are really hungry right now, and so they're probably going to revolt and start knocking my laptop around. So this got to be a fast video. Anyway, the NOR gate, you're going to put the little inverter on there and it's going to negate the output. So you're going to OR them together and then negate it. And so where an OR gate, if you are doing ORing, okay, ORing would be low when they're both low, and then if one or the other or both are high, it would be high. So it would be 0, 1, 1, 1. And then so a NOR gate is going to take that and invert it. So you have 1, 0, 0, 0. So that's your inverting. You're taking everything and flipping it. So that's what the NOR gate does. It ORs and negates 2 for 1. So how do we get our AOI logic? The inverter is really the same as for a NAND. So if you want to take a NOR gate and turn it into an inverter, you split the input and just run it into both inputs on the gate, and that should work to invert it. So if you have X or X, that's just X. So there's the OR part, and then we're going to negate it with the little bubble there, and that's going to give us X bar. So if you want to invert your signal, you just run the input into both wires there. Similar to the NAND, I don't know why I did that. Try again. To the NAND gate, you just split the input, and that will work as your inverter. So you save yourself a chip. You don't have to have a circuit with like one inverter on it. Okay, as an OR gate, NOR as an OR. So you got like the NAND as the AND gate, like the configuration. It's the same for NOR and OR. So it's exactly the same kind of configuration. The problem is when you run it through the NOR gate, it inverts it when you didn't want it to invert it. So what you just have to do is invert the output again. So this is pretty well described here. So you've got your X and your Y, and you want to OR them. That's what we're trying to do, except we don't have an OR gate. We have a NOR gate, which is going to put that pesky little inversion on the end. So it's going to give us them ORed, except inverted with the bar over them. So we don't want that. And so we're going to take that output and we're just going to split it, run it through the NOR gate, and that's going to give us our inversion. And so you have X or Y bar, bar, and of course the two bars are going to cancel each other out. And there you go. So that's how you OR it. And it's really the same configuration as the NAND with the AND. So you NANDed it, you got this inversion that you didn't want on it, and so you just run it through another NAND gate to get it back to where you wanted it to be. So it's the same concept. And when we get to the AND, the NORs as an AND gate, it's going to be the same configuration as the NANDs as an OR gate. Okay, and that's what I meant when I said they're just flip-flopped a little. So to get your NAND as a OR gate, you had to invert your inputs first and then run them through the NOR gate or NAND gate. You do the same thing here. You've got to invert them and then run them through the NOR gate. So they do kind of walk you through this. So you have your X and your Y, and what you want to get is over here. You want to get the XY. That's what we're trying to do. We're trying to get ANDing out of a bunch of NOR gates. So we start by inverting them, and so we get X bar and Y bar, and then we're going to NOR those together. So remember, like the NOR gate ORs them and then inverts them, except that it's not just X and Y, it's X bar, Y bar. And that's where they get that lovely expression. And then we use De Morgan's laws, break the line, change the sign. So we're going to break that line right there, and we're going to change the OR to an and we end up with X bar bar, ANDed with Y bar bar, Y bar, you know what I mean, Y bar bar, and then we have, that's going to be X ANDed with Y. And it's the exact same configuration that we had for the AND gates functioning, NAND gates functioning as OR gates. So it's the same configuration. Again, the better you learned it in the last lesson, the easier it ends up being for this one. This is where we stopped in class and people, I said, you want to copy this down just because it's handy. It's the same pattern. When I did it this summer, I don't think the pattern clicked because we did it so fast. Like this would have been one hour block, like the whole thing, and we just had to move on to the next project and activity. We covered pretty much the whole curriculum in 2 weeks, if that gives you any idea of how intense it was. But yeah, hopefully this does make some sense. It makes a lot more, like, just not sense, but like I'm seeing the connections better now that I'm going through it a little bit slower. So, but copy it down, pause the video if you're doing this from home, make sure that you have that. Make sure you have it clearly labeled so you don't confuse your NAND notes with your NOR notes. I want to make sure that we have those straight because you want to be able to look this up in your notebook fairly quickly. You don't want to have to go back to a PowerPoint or pull up your phone and that sort of thing. Okay, this is exactly the same thing, except that they replaced the word NAND with NOR. I think this is probably word for word the same. We have another NOR up there. So you start with the logic expression, implement it with AOI logic, and then in the AOI implementation, identify and replace your A's, your O's, and your I's with the NOR equivalent. Redraw the circuit and then look for those double inversions. Again, we have all these inverters that keep popping up in this, so you're going to have some double inversions, and then redraw the final circuit with only your NOR gates. And I think in this video, you have a much better sense of where we're going with that. So this is our example problem, and my head's covering some of it, but we're trying to implement B and C bar or A and C, and it is the same circuit. So we're going to go through the same process, except now instead of taking the gates out and replacing them with NANDs, now we're just going to replace them with NORs. And that's my little tiny one. So this is going to be a challenge here. It's just going to be a challenge. So we've got our A, B, and C. And I'm going to start with the C. Oh, actually I wanted to change the color up on that. So let's do this in blue. And so we have the inverter there, and I want to replace that with a NOR gate. So we know to do that, we're going to split the input and run it through the NOR gate, like so. And then that's going to come over, and we're going to need to AND that with B. So this is fantastic. Not really, but so here we go. In order to do that, we need to invert them first. So we got to split both of these and invert them first. So run them through, like split them and run them through a NOR. and then take that output, and that gets run through another NOR. And then we have to do the same thing with the other AND gate, and that is with, what is that with? That is with the C and A. You think like I'd have this circuit memorized by now. So C and A, and so we have to invert them. So our little split and running through the inverter, and then we're gonna NOR the output together. And then these two, what color haven't I used? Green. We're gonna OR them. And so of course we OR them by NORing them and then taking the input and splitting it and inverting it. So wow, that was awesome. It's not really awesome, and I'm sorry that my handwriting is so bad. This is not good. Okay, so that's pretty much the first 3 steps. So now we need to look for double inversions, and this is where it just doesn't come out as nice as the NAND. So we've got these inverters here, and they don't go away. There's nothing. We got to invert them before we run them through this. And then this inverter is stuck there. The only place where we have back-to-back inverters is right there. So we're really only able to replace one of them or get rid of one pair there, and everything else has to stay as is. And so our final circuit, we've got to, actually I see something else we can do, and hopefully I can remember this by the time I teach this in class. Right here, no, just kidding. I'm looking at it really hard. I don't know if my face looks like I'm looking at it really hard. No, I guess we can't. I thought for a second I saw like a spot where we had to invert something. Oh, it was here. We inverted C, and then down here we end up inverting C again. But it turns out we got rid of that inverter, so we didn't need it. I thought I saw something like in here where we inverted, but basically we're going to invert A, invert B, and invert C, and like there's not a whole lot we can do with it. So we have A, B, and C. All of these need to run through an inverter first. So there we go. And okay. So there we go. And that was this inverter on B, this inverter on C, and this inverter on A. So that's what we did. Now we need to run regular C and inverted B together. So I guess I got to do that. And those are going to go through. That's horrifying. Good grief. I can do this better. So there we go. So, and I'm actually going to do something here. I'm going to check these off just because I'm like a little, seriously. Okay, and that one, and then we just got that one. I'm basically just checking it off. And then we need inverted C and inverted A going together. So inverted C and inverted A. And that was that one. And then these two need to go through an OR, and then this is like the world's most horrific circuit. Okay, ta-da, that is awful. That's called trying to draw it with your finger on a computer screen where you don't have enough space. Hopefully you followed the process though. So now you can pause this, or you can just hang with us for the next slide, because they'll do it much neater. I think the value in this is actually walking through the process as opposed to just clicking on a slide and seeing it. Oh, here's all done out. It's a difference between seeing a worked solution to a math problem and actually going through the solution. So I do apologize that it's messy, but hopefully the process part of that helped. Okay, so this is the neater version of what we just did. And I do like their illustrations here. So, this is what we're replacing the inverter with. This is what we're replacing the AND gates with. And this is what the OR gate gets replaced with. And you can kind of see those nice, neatly drawn bubbles there. And then they replace them. And you can see the same thing we had where we had, here's the inverter, here's one AND gate, here's the other AND gate, and there's the OR gate. Okay, so there they are. And then just like ours, there's only the 2 gates that you can cancel out. Like that's it. So there's just not as much simplification on this one as there was on the NAND gate. And then this is the redrawn circuit. And this is similar to what I did, except I made the boneheaded decision to run my C like in this direction. That's way nicer, like to go in that direction. So they inverted everything and kind of cleared out some space by inverting everything at the beginning and then running the actual C value off in the correct direction to make it less cluttery. And then there's our Z output. So it's the same circuit, except way, way neater for sure. Hopefully the one that we do in class will be neater. Okay, this is the proof of the equivalence. So what they're doing on this slide, and we didn't spend a whole lot of time with this in class with the NAND gates. I am recording this the same day that we did that lesson in class, but they're tracing and analyzing the circuit. So this is C, this is B bar, and so this is going to NOR them together and then break the line, change the sign, and they're using their De Morgan's laws to simplify that as much as possible. That becomes the input right here. Okay, and you can see B, C bar, and there's the B, C bar. Here we're taking A bar and C bar and NORing them. So there's the OR, there's the bar, break the line, change the sign. That turned into just an AND gate, which we knew was going to happen. And then we're going to NOR those together. So there's the AC, you're ORing them, and then we have that. And they doesn't look like they did a step there. They could have done a step there, break the line, change the sign and stuff. But the next thing that happens is we invert it, which is going to create the double bar, which is going to cancel out with a bar below it. So there's the proof of equivalence. And again, I think I mentioned in class today that most of the proofs that you guys have seen have been of a totally different type, like your geometry proofs and stuff, even proofs that you see in calculus, like they just don't look like this. But this is another way of proving stuff, is like using known laws to show that 2 expressions are equivalent. Okay, and this is our cost analysis, and you can tell this is not as good as the NAND because we just weren't able to cancel out as many of the gates, just did not cancel out. This analysis over here is the same. You've got a lot of those unused gates, and you have to use 3 chips, and even just canceling out the 2 saved us an IC chip. We were able to do a little bit better. We had to spill over into the second chip with this one, so not as great a benefit. But if you're doing actual design work for a company, you have this option. It can reduce. Again, it might not be necessary, and most of us prefer the AOI, and most of the design work I ever did in school was AOI design. But knowing that you can design everything with NANDs and NOR gates is like a critical thing to know. And then being able to evaluate, like in this particular circuit, NAND is the better choice. In another kind of circuit, NOR might be the better choice to use. So, and again, the payoff is that it saves you money and that it reduces the number of IC chips that you have on your board. It's also kind of a pain in the butt, but hopefully you can see the benefits of it. So that should wrap this up. And the activity for this is pretty much to replicate the the voting booth activity, except you do it with NOR gates. And I'm not going to have you do as much with the NOR gates as I did with the NAND gates, because once you have the idea, you have the idea. So just stay tuned. At the time that I'm recording this, I don't know exactly what I'm going to ask you to do with it. So just stay tuned. And yeah, so there's our lesson on NOR gates.